Hello everyone, my name is Emma Brass, and today we're going to be talking about standard Brownian motion and random walks. So let's start by talking about the history of Brownian motion. Brownian motion was named after Robert Brown, who was an English botanist. And in 1827, he was studying the pollen particles of this plant right here, Clarkia pulchella. More specifically, he was studying how the pollen particles behaved in water. And he saw that they seemed to move randomly despite there being obvious forces acting upon them. He initially thought that this was an important process in fertilization and that the pollen was alive, but later recreations of the experiment using pollen from dead flowers showed the same results. This led him to come to the conclusion that something else, namely the water molecules, was moving the pollen. And this GIF on the right is just a representation of Brownian motion under a microscope. And this is actually said to be the earliest recorded physical evidence proving the existence of atoms. But before we learn more about Brownian motion, let's break it down into a simpler process known as random walks. So what is a random walk? A random walk is a stochastic or random process with each sampled outcome being independent of each other. And more specifically, we're going to be talking about pure random walks, which is the probability of taking any given direction regardless of whether it was already taken remains equal. If you think about it, that's kind of a necessary rule to have, because otherwise the favorability of one specific outcome would necessarily create infinite variables as the process continues. This is also a discrete process. So you can imagine on one dimension walking on a number line. You can imagine the number line starts at -5 and ends at +5. You can move forward or backward, but moving one specific direction does not mean that you can't take that direction again in the future. This also, as you can see, is a binomial distribution. You can imagine forward being a success and backward being a failure. And this is also represented by Pascal's triangle right here. So a one-dimensional discrete random walk can be represented as a binomial distribution. In 2 dimensions, you can imagine this little grid right here. You can imagine this is a city with each increment of length being a city block. So you can move left, right, forward, or backward, but there's no preferred direction of movement. And in 3 dimensions and higher dimensions, it gets a little trickier. 3 dimensions, you can imagine gas moving through a room. All right, so now that we talked about random walks, let's talk about actual Brownian motion. So the difference between random walks and Brownian motion is that Brownian motion describes continuous random motion of particles. And before we go further into this, I just want to clear up this W right here represents the Weiner process, which is basically just the mathematical definition of Brownian motion. So let's go through each of these here. So for all time taking on values t sub 1, t sub 2, all the way through t sub n, the n number of increments w sub t minus w sub s are independent. So what is this saying? Basically that there is no overlap between increments. This next rule right here, the Brownian at time s is equal to the Brownian at time t plus s minus the Brownian at t. This is basically just another way of saying that these are stationary increments, meaning the length of the interval only depends on the difference of the interval. So that would be t minus s. And stationary independent increments are characteristics of Levy processes. This will come up later in proofs. As you can see here from the graph, the Brownian at time 0 starts at position 0. So at time 0, position 0. And this also kind of proves the expectation. So as you can see, each increment of time that you're moving away from 0, the probability of finding the particle at that specific point is going to be 0. Therefore, the expectation of the Brownian is equal to 0. We're going to be proving also the covariance or the variance. So variance of the Brownian at time t is equal to delta t. Again, we're going to be proving that later. We're also going to be kind of going over the covariance, and we're also going to be showing how this takes on properties of a normal Gaussian distribution function. And then also the function Wt, or the Brownian at time t, is a particle's position at time t, which can also be represented by the random variable x. All right, and now let's talk about the probability density function, or PDF, of Brownian motion. So as we stated before, it's described by a normal distribution with parameters mu and sigma squared. So this is the normal formula for a normal distribution. And since we already said that the expectation is going to be 0, we know that this term on top is going to cancel out. And we know that the sigma squared is delta t, so this becomes the normal with parameters 0 and delta t. And if you just plug those into the equation, this is what you end up with right here. And you can also see here, this graph in the lower right corner most clearly resembles a binomial distribution for a one-dimensional Brownian motion. With moving left and right, you can imagine being values for success and failure. But as we already know, binomial distributions only apply to discrete random variables. So we're going to use an important theorem that relates binomial and normal distributions. And that theorem is the De Moivre-Laplace theorem. So as we know, this is a special case of the central limit theorem. And it states that as n approaches infinity, the binomial or discrete distribution begins to behave as a Gaussian or normal distribution. In other words, as the number of trials increases, a one-dimensional random walk begins to resemble a Brownian motion characterized by a normal distribution. And this can also be proven similarly, as I said, with the central limit theorem by analyzing the moment generating function of a random variable that has unit variance and 0 expectation. All right, so now that we talked about that, let's talk about variance and covariance. So Brownian motion is a Levy process, and basically what that's saying is that it has stationary independent increments. The subscript n represents the time interval t sub 2 minus t sub 1, and again, we know that that is a stationary and independent increment, so no overlap. The random variable x sub n is the particle position at time n, or the Brownian at n equals delta t, which again, delta t is this right here. So as we know from previous calculations in this class, the variance of a random variable is equal to the expectation of that variable squared minus the expectation quantity squared of that variable. And we know that the expectation of a Brownian motion is always going to be 0, so this term cancels out, and we're just left with the variance equaling expectation of quantity x squared. And we know for a continuous function that this is going to be an integral. So it's going to be t squared f of t dt, and f of t is just the PDF that we previously defined. So once you plug that in, you get the result being delta t, and you're probably wondering how I made this jump right here. Basically, if you just express alpha as 1 over 2n, then that becomes the Gaussian integral function from the previous proofs in this class. For covariance, this follows a similar calculation with covariance of u v equaling the minimum of u and v. This right here is just a really useful MatLab code. It's not one that I made myself, but it's one that I found online from John Burkhart's Brownian motion simulation test code. And basically, this right here is just coding for the color of the line, and it's basically making just you can repeat this with as many simulations as you want. I did it with 5, basically using this same format right here, and you can repeat it as many times as you want. It's just really helpful to be able to see basically an interpretation of Brownian motion in a simulation. And as you can see here, the particle at time 0 begins at position 0. And this is for over a period of 1 second. So what are some real-world applications and other theories of Brownian motion? It's actually one of the most common processes used in analyzing movements in the stock market. So Brownian motion is a stochastic random process, but its behavior can be predicted similarly to how futures in the stock market can be predicted. So not necessarily set in stone, but you can kind of predict what its movements will be. And in 1905, Einstein actually used this process in the molecular kinetic theory of heat. I kind of touched upon this earlier when I was discussing how it was the first recorded evidence of the existence of atoms. But basically what this is saying is that as heat increases, movement of particles increases, which is supported by Brownian because it's more exaggerated at higher temperatures. And to an extent, this also describes the process of diffusion. However, as you can see from this little illustration that I made, diffusion right here is demonstrated by this illustration. So basically diffusion requires a concentration gradient for a specific motion of the particles that you're examining. And then right here, this is Brownian. So there is no concentration gradient. So there is no desired flow for the particles that you're examining. And these are my sources. Thank you.